I'm going to work this example for you of analyzing and graphing this particular polynomial. So the first step is always see if there's a GCF, especially if the first coefficient is negative. I want to factor that out. But as I'm looking at these coefficients, 6, 42, 12, and negative 84, if I know my times tables a little, I should recognize that they're all divisible by 6, or I can check on the calculator, which I actually did. So I'm going to take out a negative 6, which leaves inside, there is no x term that's common, so an x cubed minus, let's see, 42 divided by 6 I think is, oh goodness, 8, no, all right, let's do it. 42 divided by 6, 7, x squared, and then this one is going to be minus 2x, and this one's going to be plus, yeah, I have no chance, 84 divided by 6, 14. All right, so this is the new polynomial I'm going to analyze, and I need to recognize that the graph is going to follow this, it's going to be reflected and multiplied by 6, but for now I'm going to focus on this piece of it and try and factor it further. So if I want to really be smart, I'm going to follow this process, and I'm going to analyze the signs next. So I'm going to take a quick look just inside here. I started positive, this term is positive, then I go negative, so that is a change. That is one I'm going to count on my sign changes. Staying negative, I don't count, but then going positive, I do count. So this tells me that there are 2 or 0 positive real roots. And that is Descartes' rule of signs for positive roots. Now I'm going to analyze, if I were to plug in a negative x, this sign would change, this sign would not change. So I would have a negative, and this would stay a negative because negative x squared is still positive x, and so the negative stays. This one will change to a plus, and this one can't change based on what x is. So now I have negative, negative, positive, positive. So I have one negative real root. And I can't have 0 because if I have any, if I have 1, it has to go down in pairs because of the nature of irrational and complex roots, which we know from using the quadratic formula. So 2 or 0 positive roots and 1 negative real root. I might start looking in the positive, except there's a chance that I won't find one. I'm guaranteed to find one in the negative. So I might start by choosing a negative thing. I'm going to take a note over here, 1 negative and 2 or 0 positive. And then I can erase and make more room on my paper. But this was my sign analysis. And my next step is going to be to start a little bit of a graph. I'm going to graph only this part, and then at the end I'm going to stretch it and flip it with that negative, because what I'm trying to analyze now is just this. Can I break that up? And anything I do in dividing that is going to look like this graph, not like the flipped and stretched version. So just a quick little sketch. My leading term is x cubed, and it's positive inside the parentheses. So my end behavior is going to look like this and this. A cubed is odd. 3 is odd. This is a degree 3. So the end behavior will be like a y equals x line or like a cubic parent, and there is no negative to flip it. So there's no transformation on that. It just looks like a cubic parent. Now I can also find my y-intercept if I wanted to. So for this particular function inside the parentheses, my y-intercept is when x is 0. So 0, 0, 0, 14. I have a positive y-intercept. That might turn out to be handy later, so it's always worth checking. All right, so I started my graph, I analyzed my signs. Now I'm going to make a list of the possible factors of this cubic polynomial. For that, I'm actually going to start my division sort of process here. And at the end of the process, I'm going to want this to be 14. I'm not going to fill it in because I'm going to do some division on this. This is sort of my format for doing the division. And I will only know if I win, if I found an actual factor, if this box turns out to be 14. But if I want it to be 14, I'm going to need a number here times a number here that give me 14. Since I'm only looking for whole numbers in this process, that means I can break my 14 into a 2 times 7, and that could be a +2 times a +7, or a -2 times a -7 would both also give me the positive 14 I'm looking for. So this is ±2 and ±7. But similarly, I could have 1 times 14. Now these are the only factors of 14 because there's no way to break up my 2 or my 7 into other pieces and move them around. So my list of possible factors, possible 2 S's, is going to be x +2, x -2, x +7, and x -7. And then I'm going to also have x +14, x -14, x +1, and x -1. Now, with all of those, I have a 0 that goes with them. What x makes this 0 is a -2. What x makes this 0 is a +2. This one goes with the 0 of -7. This one's +7. This one's -14. This one's 14. This one's -1. And this one is 1. So, sorry. Let's see here. So I am guaranteed to find one negative root. However, well, let's go ahead and try one and see what happens. Actually, I really like trying positive roots because I can use the whole sign analysis to see if I've capped it out or not. So I might go ahead and try dividing this polynomial, the underlined polynomial there, by something middling, maybe like 2. I'm going to test this one right now. So I'm going to divide by x -2, and I'm looking to see at 2 what's happening on the graph. This division will answer exactly that question. It'll either tell me if my remainder is 0, it'll tell me it's a 0, and I can put this point right here. But if the remainder is not 0, I have to put the point at wherever the remainder is. That's the remainder theorem. So I'm going to do the division. I wanted x cubed, so x squared times x gives me the x cubed. And I get x squared minus 2, -2x squared. Sorry, not x squared minus 2, x squared times -2. Because I'm finding the area, so I take the width times the height. Now I want 7x squareds, -7x squareds, and I have -2. So I need another -5x squareds to finish out my -7x squared. So to get this, I'm going to need to multiply my x height by -5x wide. And Now that I have the width, negative 5x, I multiply that by negative 2 to get a 10x. Now what I want up here is negative 2x, but I have 10x. I'm going to have to subtract 12 x's to get from positive 10 to negative 2 x's. Now, if I have 12x, the height of this is x, so negative 12 is the number I get here. Now, as I'm looking ahead, I can't possibly get 14 from negative 12 and negative 2, but what do I get? I get a positive 24. Now, this is not 14, so I'm going to continue the process as I have been before, where I add in what I need in the diagonal in order to force it to be exactly this. So to get to 14, I need to subtract 10, which means at 2, my function value is negative 10. That remainder is the value. Now, I can always check that by plugging in 2 here, 2 cubed minus 7 times 2 squared minus 2 times 2 plus 14. It will give me negative 10. I'm not going to do that on this video, but you can go ahead and pause and try it. Remember, I'm not including the negative 6 right now. I'm analyzing without the GCF so that I can factor this one big factor that I have. So, that told me some information. Now I tested a positive 0. So I'm also going to look for whether my signs up here tell me that I've capped it out. I want to know if should I look below it at 1 or should I look above it at 7. Now to be an upper bound, I need all positives. Well, I can see right now I do not have that. So what I do know is that 2 is not an upper bound, which means I might have another 0 that's bigger than 2. I'm going to take a quick minute to graph all of these zeros, or you sort of list them on my axis here. I had a 1 and a 2 and a 7 and a 14. And I also had those in negative. So negative 1, negative 2, negative 7, and negative 14 way out here. I'll make it way out there. So I have this point, I have that point. Oh, there is probably a 0 between here. That's weird. I mean, it says I have 2 or 0 positives. I might have 2 because my graph needs to connect these 2 dots that I've made. Maybe it's at 1. But I also have a situation where I know my negative 2 is not the upper bound, or my 2 is not at the upper bound, and I know my end behavior is going to force me to go up this way. So either I'm going to cross at 7 or 14 or an irrational number. So one of these zeros could be irrational. But they're not imaginary. There's definitely 3 zeros here because I have to get to that end behavior. I have to get to that end behavior. So somewhere I'm going to cross twice in the positive, just like my sign analysis said. And somewhere I'm going to cross in the negative, just based on my y-intercept and this one point that I found from my quote-unquote failed division. That remainder gave me a lot of information. So now I'm going to be looking for the actual real 0. There are 3 of them. And I don't know which ones, if any, are rational. So, I think I'm going to try 7 next. I'm going to try 7. So 2 was not, it did not work. But it gave me information. So I'm going to try 7 next, which means I'm going to change all of this. I wouldn't, if I were you, I would not erase. I would draw a new box, but I'm in limited space. So you should draw a new box. But I'm going to try x minus 7, which would glean me a positive 7, 0. So So if I do that, then I have x squared, negative 7x squared. I need negative 7. Oh, gosh, that's funny. I need negative 7x squared, and I already have it. This is an interesting scenario where technically I need 0 more x squareds. Now, I could put a 0x squared here, but that would make this 0x, right? And this would become 0, just all zeros all around. And the next thing I need is negative 2x. I mean, this is 0x's, so I need a negative 2x to go here. You could skip this row entirely, recognizing that I have all the x squareds I need, and the next step would be to find my negative 2x. So you could have put it here, and it'd just be a smaller box. But I want to be clear that when you have what you need, you just add 0. That's a good thing. But then you need to remember that you need the negative 2x. I have 0x's, I need negative 2x's, so I put that there. Which means this is a negative 2, right? The width is got to be negative 2 if my height is just x. So down here I have a positive 14. I win! Yay! So what does that mean? It means that this whole thing, this degree 3 polynomial here, can be rewritten as the linear factor x minus 7 times the quadratic factor x squared minus 2. This is exciting. I have factored this. I want to bring my negative 6 down here with it to make sure that I maintain the original problem. But I also, on my graph, found that there's a point right here. So this actually technically goes through there to infinity. Am I done? No, I needed to graph. I needed to fully graph the whole function, or at least all the zeros and some end behavior. So I need to find those other zeros. There's 2 more real zeros that I expect from my graph. So how do I factor x squared minus 2? There's a couple of different ways to think about it. Just like I can find that my 0 is 7 by setting x minus 7 equal to 0, I'm going to set my x squared minus 2 equal to 0 to find the 2 zeros that this will give me. And the easiest way to undo this is to actually, because there's no linear term, I can isolate my x squared and then take the square root, making sure I recognize there are 2 square roots of 2. There's a positive and a negative square root of 2. And that makes up for my positive and my negative zeros right here. They're irrational, so I was never going to find them from my list. These are only the rational factors, and these 2 are irrational. Notice that they come in pairs when I use the square root. Now, I could also have used the quadratic formula. That's what I kind of want you to be aware of. I need to solve for my last zeros, and now that it's quadratic, I have all my quadratic tools. So I can say A equals 1, B equals 0, and C equals negative 2. So the opposite of B, plus or minus the square root of B squared minus 4 times A times C, all over 2 times A. Well, the 0 term can just go away, right? It disappears. So I have plus or minus the square root of, now the minus 4 and the negative 2 together make a positive 8 all over 2. If I simplify this radical, it's plus or minus 2 square root of 2, because 8 is 2 times 2 times 2, and so 2 of those 2's get to come out, or 4 times 2, and the square root of 4 is 2. Over 2, and that makes a 1, so I get plus or minus the square root of 2. Still the same answers I got for using the square root method. Now there's a third method that I do want to share with you. This is a difference and x squared. I can use the difference of squares formula that says that anything squared minus squared is the original unsquared minus the thing unsquared times the original plus the thing unsquared. But since 2 isn't a perfect square, I have to take the square root of it. And this leads to the same result. When I say x minus root 2 equals 0, then x equals positive root 2. When x plus root 2 equals 0, then x equals negative root 2. The same two answers that I got through the quadratic formula and earlier by just isolating the square and taking the square root. So just be aware, a quadratic will always have two solutions. In this case, they're real and irrational. In some cases, like if it was a plus, these would be imaginary. Okay, but it's not. So this is my function. I need to fully factor it. I'm gonna write it all up here underneath my original. The final official factored form is -6 times x minus 7 times, I'm gonna go ahead and linearly factor x minus square root of 2 times x plus square root of 2, because those are my irrational zeros. And this is my final factored version. I can graph by plotting the negative square root of 2, the positive square root of 2, and 7, and knowing my, oh, I forgot to flip. Uh-oh, there was a negative here. So in my original problem, my leading coefficient was negative. So I'm gonna erase all my work in the meantime. Even my 0 is different because I flipped everything upside down. So I'm gonna flip it upside down. My zeros, though, when I multiply all of this by negative, at the zeros, they don't change. Because when this factor is 0, the whole thing's 0, whether it's positive or negative. When this factor is 0, the whole thing's, etc., right? So once I'm in zeros form or factored form, the positive and negative doesn't matter on the axis, but it does matter overall. So my leading term says negative with an odd degree. So even that point got moved. Negative with an odd degree leaves here, and all of my factors have a multiplicity of 1. So I'm gonna cross right through them as if they were just part of a line. I'm gonna start at my end behavior, go down through here, up through here, and down through here. This is what my graph will look like, where this is square root of 2, this is negative square root of 2, and this is 7. And by the way, here's the Desmos. Looks a lot like mine, huh? Kinda, sorta. It's higher, right? It goes up to a maximum value of almost 300, 277. But the zeros are negative square root of 2, positive square root of 2, and 7. Hope that helps.